One of the nice applications for vector-valued functions would be looking at projectiles, things that are going up and then landing down, and so we have gravity and stuff like that as part of what's happening. Then we can try to model motion in space or in 2 dimensions that would make use of some of the physics that you may or may not have heard of before. And so let's take a look at start with 2-dimensional projectile things that are happening, and we're going to look at this from the point of view of vectors. So in 2D, we're restricted to just I and j, the x and the y axis. And so what we could do is we can imagine something happening here. Maybe we have a ball that's going to get shot out from the ground at 0, and when it gets shot out of the ground, we would imagine this thing like that game that I told you guys about called cannon fodder or something like that, where you find an angle of inclination and then find a speed of an initial velocity. So the magnitude of that gives you the speed. And what we could do is, once we have that information and then we start off with the gravity, then we can tell everything about this particular projectile. So say given speed, and a lot of times they just call it v naught without an arrow on top. Remember, the arrow on top makes it a vector, and then if you take the arrow on top and with a magnitude, it just means it's a scalar. But sometimes they call it v without the magnitude or the vector. And so in the book it's clear because the vector is bold-faced and then the v is italicized, so you can kind of tell the difference. But if you just see the v naught without the arrow, let's assume it's a scalar, and let's assume it's the magnitude of the vector v naught. An angle of inclination theta with gravity, we can find the path of the projectile. So we start by identifying the gravity, and let's say the gravity is what is it, 9.8 meters per second or something like that. Meters per second squared. They just use s for seconds, right? But since we're now talking about vectors, reporting your gravity as a scalar is not enough. It's not good enough. So we actually want to report it as a vector. Now, our gravity is just pulling downward. So we know that the downward direction is the y direction, and it's down, so it's negative. And then it's not moving along any x. There's no acceleration in the x direction. So we can just say that acceleration vector, and we'll call it a vector, is equal to 0 in the x direction and negative 9.8 in the y direction. So we can begin with this information as your information about your gravity, or your acceleration. And we know that if we integrate That's not an integral sign. That's an integral sign. If we integrate, then we're going to get the velocity. And then if we integrate again, then we're going to get the position. So we do some integrals, and we get the velocity function. And we can go ahead and integrate this with respect to t. The 0, a constant with respect to t, is just going to be a 0. The antiderivative of 0 with respect to t is going to be a constant. So we can call it constant, I don't know, C1. And then we get negative 9.8 t plus another constant C2. Actually, I should have done this a little bit differently. Maybe I'll redo this. And there might have been a previous step over here that you might want to consider, that this is actually 0, negative 9.8 times t plus a constant vector that has a constant in x, constant in y. And so if you look at C1 comma C2 as this vector, and then the other one multiplied by the scalar t, this is what we would get. Okay? And this vector if we remember back in Calc 2 when we did some integrals from acceleration to velocity to position, the vector, the constant c that comes out of there happens to be your initial velocity. So we can note that the vector c is the initial velocity. And if we can somehow identify this vector that we drew up here as the initial velocity vector, then we can replace c with that initial velocity. So we may need to call this is your initial velocity. And what we're going to need to do is we're going to need to identify our initial velocity. Now this is v naught with an arrow on top as something with an x and a y component. So if we have the length of that vector and the angle of inclination, can you figure out your x and your y values here? Okay, if you think about it really hard, you can find it. If you've taken physics before, you probably know it already. But if not, you can just derive it. The components of that vector is just an x and y value, and if you drop this perpendicular down, you get a right triangle, right? And so it all stuff that has to do with sines and cosines. So your initial velocity is actually the speed times the cosine for the x component, cosine of the angle, and then your y is the speed times the sine of that angle. So that's what c turns out to be. Okay, so we can further rewrite this as, instead of c1, it's the first component of your velocity That's your speed times the cosine of the angle, comma, negative 9.8 t plus v naught sine of the angle. Okay? This is a sine. All right, now if we keep going, just do one more integral here to get the position. And the position, a lot of times people call it S, or sometimes people call it X, or sometimes people call it R. So regardless of what you call it, I'll call it R. It means a position, which is antiderivative of the velocity, or the antiderivative of the velocity S. So if we take this and take the antiderivative of this, we're going to get 1/2, if you remember the formula for your integrals, 1/2 0, well, I guess I should do this in pieces. Since we have this already, let's just go from here. So the position then becomes v naught cosine theta times t. So v naught cosine theta is just the number. Once you know the speed and the angle of inclination, you can just put that into the formula and get a number. And then you multiply that times t, and then here you're going to get your extra constant. Let's call it r sub 1. And then your y component is negative 9.8 t. The antiderivative of that is half of 9.8 is 4.9? 4.9? T squared plus v naught sine theta times t plus another constant, let's call it r2, where r1 comma r2 is the initial position. So in our simple example here at 0, 0, then that is just an initial position where it's 0, 0. And once you have this, you really know everything there is to know about the projectile. You know its highest point. You know the high point is the maximum y value, so you find when the maximum is equal to 0. You can find the range where it lands. So this projectile would be shooting something, and you can find where it lands by setting, finding out when it's going to hit the ground. It's going to hit the ground when your y is equal to 0. So whenever it hits the ground when your y is equal to 0, you just find the x distance there. Okay? And anything else you need to know? How fast was it going when it hit the ground and things like that? So let's do a quick example of this projectile. Yeah?
So is the path the position? Or
The path is the position.
okay.
So the path is your position of the projectile at any time t. So we can figure out when it hit the ground, when the highest point was, what the highest point was, how far did it go, everything. So this is a formula that's kind of memorized in physics, but I'd like to think of it as something that you should be able to rederive every time until you've memorized it, and then it becomes now beyond just a formula to try to memorize, then you'll actually know it. All right, so let's take this information and let's put a projectile maybe shooting from the ground, or it doesn't have to shoot from the ground. We can have the projectile shooting from a platform, and then let's see how far it goes or something like that. Oh, we can have it shoot from the ground. It doesn't matter. All right, let's do an example. You have a cannon shooting from the origin. Makes it simpler. With an angle of inclination, theta is equal to, well, let's just do 45 degrees. 45 degrees. And then a speed of 100 meters per second. So we can ask the common questions: what's the highest point, and how far will it land? And then we can start from the beginning, or we can just kind of cheat and take a look at the formula. I suggest you start from the beginning, but I'm not going to, because I'm just going to jump to the formula where we have r, the position. All right? So I do want to know what the initial velocity is. And the initial velocity, if you remember, is the speed times cosine of the angle and speed times sine of the angle. So the speed is 100 meters per second times the cosine of 45 degrees is root 2 over 2. And then the y component is the same. It's a sine, but the sine of 45 is also root 2 over 2. So this is your initial velocity. So according to this information, our speed, or our position function, is the velocity, the x velocity. So this simplifies to just 50 root 2 times t plus the initial position here. It's starting from the origin, so let's just call it 0, 0. So this thing is just 50 square root of 2 times t with no extra constant, and then negative 4.9 t squared plus 50 root 2 times t plus 0 again. So those constants that would have normally gone at the end of that, of each of those components, would have been 0. So this is it. Now that you know this, you have all the pieces of information you need to know about this projectile, including the highest point and where it would land. How do you find the highest point? Velocity 0. So the velocity, it's always moving along the x-axis. If you look at the path, it's always going to be moving along the x-axis. But the y is going to go from positive to 0 to negative. Not positive, but the direction of that. So the velocity goes up and then it goes down. So at some point we reach our maximum. And that's dependent on the velocity vector's y value. So y prime for the y component is going to equal to 0. So we need to take the derivative of this. Y prime of t is equal to negative 9.8 t plus 50 root 2 And this is a nice linear function, which means we can easily solve for it by just isolating the t when you set it equal to 0. So we got a couple of negatives, negative when you bring it over, negative from 9.8 when you divide, so t is equal to 50 root 2 divided by 9.8, which is about, anybody with a calculator? .2 seconds. Oh, we should confirm that. Always want to confirm with one other person. Anybody confirm this? Yep, we got a nod, so we'll go with that. So this is not what we're looking for. We're not looking for when. We're looking for what is the actual highest height. So what we want to do is we want to take this number and then plug it into the height, which is the y value. So the height is going to be y, not the prime, but the y itself, evaluated at 7.2. So I guess if you want to be precise, you can put this whole fraction in. Maybe I don't want to be precise. 4.9 50 root 2 over 9.8 squared plus 50 root 2 times 50 root 2 over 9.8. Or you can put 7.2, I suppose. And then whatever this turns out to be will be your answer in meters. Maybe you should just put a 7.2 there. The thing is, depending on the problem, especially if you're working on the homework problem in the computer, they might want your final answer to be precise. If they want your final answer to be exact, then this is what you need to do and maybe simplify a little bit. If they want it exact to 2 decimal places, then since 7.2 is an intermediate calculation to get to your final answer, you may need to put as many decimal places here as possible, like maybe up to 8 to 9 decimal places to put in here or something. So an algebraic, computer algebraic system might be good, like Mathematica or MATLAB or something. All right, do we get a number for this? 255, 254. Is that right? Is that what you said? 0.1. So depending on what you use, whether you use the actual value or you put 7.2, you might get 254. Again, the calculation of what you want at the end is important to what you do in the middle. All right. So that's the height, and then the range would be the distance that you're going to land. How far away is this? And the distance is probably going to be whatever it is. So how would we find the distance? How would we find where it's going to land? What? Oh, I guess it's a parabola. Yeah. But say if this was a little bit off, if this was higher, then you don't just double it, so it's a little trickier. So what's a more surefire way to find out where it lands? Anna? Did you have a... Yeah? Oh. Y equals what? Sorry. Y equals 0. At least it lands on the ground when y is equal to 0, right? So it's going to land on the ground when y is equal to 0. So you're going to set the y value equal to 0, and one of the t values you should get out of that is 0, because it starts at the x-axis. So you're going to set y equal to 0, and that is negative 4.9 t squared plus 50 root 2t. And then if you set that equal to 0, you can factor out, let's just factor out a t, negative 4.9t plus 50 square root of 2t equals 0. And t is equal to 0 is one solution, which I said should have been there. That's where it starts. And then when you set this equal to 0, then you'll get your other solution, which is probably going to be twice as much as this. And if you look at this, your other t value is 50 square root of 2 divided by 4.9, which is double of this. So now, to find the range or find out how far this is, what do we do with this time? Plug it into x. If you plug it in for y, you're going to get 0, right? Because that's what you just solved for. So you need to plug that in for x, and that'll tell you the x distance, which is what you're looking for. So range is going to be your x value evaluated at that point. Let's call it 50 root 2 divided by 4.9, approximately 14.4 or something. And that's 50 root 2 times t. That's just, that's pretty simple. And let's hope we get a positive number. That's whatever. So, anybody figure this out? 1,020. And this would be in meters. All right, that's it. Any questions? If it doesn't start at origin, it just affects the position, correct. But all this stuff, all this stuff is related to the position that we're solving for, so you got to make sure you put those things in there. Okay, let's do another one. I'm just thinking about Steph Curry and the basketball game. Actually, I had a couple of things I was going to show you, but I didn't prepare them. I got this Facebook post that somebody sent me, and it was some guy shooting baskets and then couldn't shoot. And so they decided, he sat down and wrote formulas down, and then he shot and made all the shots. I don't know. They didn't show it. I'd pull up my Facebook page, but I'll try to dig it up and then post it online. Anyways, let's do an example where he was going from left to right. Let's go from right to left just to make it a little bit easier. And the basket hoop is like 10 feet off the ground, right? And his last shot was like 38 feet away. So let's make up a couple of things. Let's make up the height of the ball when it leaves his hand. How tall is he? 6'2", 6'3". So if he jumps, maybe the ball would leave his hand at 7 feet. Maybe more than that.
Well, if he doesn't have it.
Yeah, if he doesn't jump. So let's say he starts off at 7 feet tall, or the ball leaves his hand at 7 feet. So the initial position, the ball is our projectile, the initial position is going to be 7 feet. And let's say he threw it with a little bit of an arc, so I'd say it's more than a little bit, slightly more than 45 degrees. So let's make up an angle. 46. I'd go 60 maybe. I was going to go 50, but 60 sounds good. So let's ask the question from here, what should the speed of the ball be for him to be able to make this shot? So let's find the speed to make this shot. So this is just kind of out somewhere in different places. So let's actually put this on an axis. And I think the easiest thing to do is make this basket right directly as your y-axis. So it looks like our end goal here is going to be, we want this ball to hit at the point 0 for x and 10 for the y, right? And then when we begin the problem, we need an initial position, initial velocity. So what will be our initial position? So our initial position, 38,7. This is going to be your R naught, we call it, but we'll just use those numbers as going to be the constants after a second integral. And then our initial velocity, since we have an unknown v, not an arrow, so we have an unknown speed, that's what we're solving for. We're going to have that speed there, but we know at least the cosine of 60 and the sine of 60, right? What's the cosine of 60? 1/2. So it'll be v naught over 2, and the sine of 60, 3 over 2. So v naught root 3 over 2. This is your velocity vector that has those components. And we begin this with the gravity. And we're dealing with feet now. I changed from meters to feet, so we have to go 32, is it? So 0, negative 32 would be your gravity. All right, so the picture should have told you all this information. And now that you have all this information, you should be able to do the problem. Since we really only care about the position, we'll go ahead and integrate. I was going to ignore the integrals and do that, or but let's just go through the process. So given your acceleration vector, you can find your position, your velocity vector, by taking the antiderivative. And remember, the constant to come out of that antiderivative is just your initial velocity. So I have v naught over 2 and negative 32t plus, let's write square root of 3 over 2 v naught. That's your velocity. Did I do something? Yeah? Oh, in feet per second. Because we're dealing with feet per second squared. We're dealing with feet now instead of meters. So this is your gravity in in U.S. standard or non-metric form, whatever. Yeah, I know, huh? In a difficult way. But isn't it England? It's the yeah, it's the imperial standard. So it's one of the kings decided to redo the measurements or something. I don't know. All right, so this is your velocity. We go to the position by integrating again. R of t is v naught over 2. Remember that v naught over 2 is just really v naught times the cosine of the angle. And so that's the angle. So this time we have a position. It's not just 0 anymore. Our initial position, at least for this, is 38. Oh, wait, there's something wrong here. Sorry. What's wrong? What did I do wrong? Well, I'm going to do it right now. But there's something wrong up here, and actually it might have been something wrong up here. No. The plus constants will come out of here when we do the integrals. So I did something wrong here. You know what I did? No? Not 0. No? Okay. So this whole picture business over here works really nicely if you're going from left to right. Yeah, since we're going from right to left, the y is still going upward. That's still okay. But now the initial velocity here has to be going negative on the negative direction. So negative of that cosine will give a negative number. And so that would have got us in trouble. That would have shot this way, and we would have not gotten close to getting 0. All right, so we got the 38 as your initial x constant position, and then the 7 will come up here when we integrate this. So it's negative 16 t squared plus root 3 over 2 v naught t plus now your 7. So now we have this completely done. So at this point, there's 2 ways to approach this. And now that we've corrected our negative sign for the velocity in the x direction, we know that this graph will eventually, or the projectile will eventually hit x is equal to 0. All right, so that's what we're going to shoot for. We're going to shoot for letting x equal to 0. And what we're going to do is we want the position to eventually equal to the hoop, 0, 10. So what we're going to do is we're going to set that position vector to 0, 10. We will have 2 equations to deal with, and we're also going to have 2 unknowns. We're going to have the t, and then the initial velocity, which is what we're looking for. Okay? So we're going to put these 2 together and hopefully come up with a solution. So putting these 2 together, this looks like it's going to be an easy find because this is linear. We got negative v naught over 2t plus 38 is equal to 0. So let's go ahead and solve for that. I thought I picked green. So we can solve for t or v naught. Let's solve for t. T is equal to negative 38 over to the other side, and v naught over 2 goes to the other side as 2 over v naught. And then the negatives would cancel. And so what do I have here? Oh, it's 38 times 2. 60, 70, 76. Okay, And now that we have that, we'll put that in to the y and say this is the time that it's supposed to land on x is equal to 0. And so we want to just make sure we want to find it when the height is equal to 10. So let's put 76 over v naught in for t. So I got 16, negative 16, 76 over v naught t squared, or not t squared, 76 over v naught squared plus root 3 over 2 v naught times 76 over v naught plus 7. And then we want to force this to equal to 10, which is the height. I'm not going to be able to do this by hand for too long, but I can see some things that will cancel. And then I have what's 76 squared? Ooh, I don't know what that is. And then multiply by 16. So I got that big number. 2 into 76 is it's 38. Oh, this one? Yep. These two v naughts cancel. I get 2's cancel with 76. This is 38. Root 3 plus 7 equals 10. I suppose let's bring the 7 over to the other side. 3. And then just continue to solve for v naught here, I guess. We have to do some reciprocal stuff. Multiply by -1. So we got 92416 over v naught squared. And I'll bring this over to the other side. This multiplied by -1 will become positive on the other side. 38 root 3 minus 3, and this will become negative. And then I have to do the reciprocal. And then take the square root of that. All right. So what's the square root of this? What's this with the square root? Anybody? Say again? 38.4 feet per second. So Steph Curry needed to shoot this with an initial velocity of 38.4 feet per second to be able to make that shot with his given angle, 60 degrees. Go, Steph. Okay. Any questions? So this time, instead of starting by giving you the information about the speed and angle of inclination, you have to find one of them. You have to find the angle. Well, you're given the angle. We need to find the speed for you to be able to hit a particular target. Okay. So that's kind of like working it backwards. But if you understand the different components of the velocity and the position function, you should be able to answer any of these weird questions by resetting up your integrals from the acceleration to the velocity to the position and putting in the information correctly, the correct initial position and initial velocity. And then if you have all those numbers fixed up and worked out nicely, then you should be able to answer any question about this particular problem. Projectile. All right, any questions?
So when the ball goes to the right, from right to left, we have to put negative sign.
Yeah, just because of the way the arrow's pointing here, if we put this on an x-axis, you know, the angle of inclination that we're looking at is over here. We have to make sure, since it's pointing this way, we have to make sure that the x value is actually less than 0 because it's going in this direction. So just make the x value negative, and then you'll go in that direction. Any other questions? All right. So that's in 2 dimensions, and really when you talk about projectiles in 3D, it's essentially the same business, except you don't have a nice fit formula like this, and the problem might need to give you a little bit more information instead of a speed and the angle of inclination, because the angle of inclination is a nice way to describe things that are 2-dimensional. But then when you're talking about 3D, there's several angles to consider. And so to consider all those different angles might be a little bit more difficult than what it's worth. So a lot of times the problems would just give you information about initial velocities and initial positions. So let's do an example in 3 dimensions. And so we can make up a problem where you're shot off of a cannon, maybe? No? Say you're driving along a cliff and then you fly off. Does that sound like fun? No? What? Oh, just say you're riding in my car and then I accidentally hit the eject button for the passenger, and then you came flying off a cliff. Let's do that. You can be in a roller coaster and you fly off.
Why am I flying?
Just because you're a projectile. Well, we could just throw a ball out. Is that better? Trying to imagine the basketball in 3D. That's a little bit more difficult. Yeah. What were we doing?
We were killing them.
Okay. Killing you softly. All right, let's draw a cliff. Let's draw a car and a cliff. I used to have a truck. And then your seat being ejected. Oh, that's all confusing. Let's try it again. All right, so we need to give you an initial position. Really, that's the only thing that's important here. Initial position and initial velocity. So let's say the cliff was we need an axis. Let's put the axis, if we put the axis directly above you, that would make things a little bit easier. And I'm going to draw my axis a little bit differently than what I normally would. So if we put the initial position at 0, 0, 0 for x, 0 for y, and some height of the cliff, say 100 feet. Are we doing feet or meters? Does it matter to you? What? Meters? So let's do 100 meters as your initial position. And for initial velocity, we need to get you off going in a three-dimensional vector direction. So for this, because it's hard to play around with angles in 3 dimensions, normally would just give you the actual angle or the actual velocity vector. So let's give it a velocity of, this is meters, maybe 20 meters in the x, meters per second, sorry. 30 meters per second in the y, and it needs an upward thrust also. Let's bump you up to 50 there. So your initial velocity is going to be 20, 30, 50. And then you want to know where you're going to land in the ocean. So assuming that the ocean is at sea level, assuming the sea level is when z is equal to 0, you're actually trying to figure out when you're going to hit the xy plane. And then maybe we can make this a little fancier and have a little net out there waiting for you. Because if the net doesn't catch you, then there's going to be a bunch of hungry sharks going after you. Okay, so let's see where you land. If we follow through the same process, without memorizing that formula, remember, then this would just be just another projectile, acceleration to velocity to position exercise, right? And then the question we're asking is when you're going to hit the ground. So that's like instead of y equal to 0, it's a z equal to 0 business. And then you'll find your x and y components. All right, so let's do it. So we'll start off with the acceleration a of t. It's constant acceleration. Oh, unless maybe you get strapped with a rocket pack, and maybe it gives you some Magnus force along the x direction. Let's not worry about that.
Well, that would be along the xy direction.
Yeah, so a force along the x direction would be pushing you. Have you seen that somebody threw a basketball on one of the dams and they spun it? And that spin gives it a Magnus force that makes it go not just directly down, but it starts going and curving. And the further it goes down, the faster it curves. It's an interesting video. Anyways, like baseball, when you hit a ball, right, it doesn't, or when you throw a curve, when you hit a ball, sometimes the ball curves, or a golf ball, it has a slice or whatever it's called. And so that happens, that's called a Magnus force when it starts curving. It doesn't go in a direction you hit it. It starts curving a certain way. It's because the ball has a certain spin, and it's going to take that spin. So that's another form of acceleration that could happen, but we're not going to do it here. So in this case, our acceleration is just a 0, 0 in the x and the y components, and then it's just a downward acceleration. So you're just going to get pushed, and you're going to go in that direction that you're being pushed. And also this neglects air resistance and all kinds of other stuff. So this is just in a perfect world. I get to eject you from my truck.
This is recording, right?
Damn. Yes. All right. I've had a couple of recordings where it accidentally didn't record the audio for some reason in my past lectures. Anyways, to get from acceleration to velocity, we integrate, and because of these nice functions, because our acceleration is constant, when we integrate, our constants that we're going to come out with is just going to be your components of your initial velocity, right? So 0t plus 20, 0t plus 30, and the integral of negative 9.8 is negative 9.8t, and your constant that will come out of here is 50. And if you just want to remind yourself that when you integrate this, you're going to get essentially your acceleration vector plus your initial velocity. And so that's how you get the components from your initial velocity. And we'll do the same, and we'll get the information about your initial position. Let's call this R, T, for your position. Antiderivative of 20 is 20t. Your constant is your initial position this time. The velocity, the initial position is 0 in the x. 30t plus your initial position in the y is 0. And then negative 9.8. Oops, let's call it 4.9 since we're dividing it by 2. And then your initial position here was starting from a cliff that's 100 meters up. Okay. So now let's figure out when you're going to be at sea level. So you're going to go up, you're going to follow its path, get down to sea level when z is equal to 0. So let's find out the sea level business. Hit the ocean when z is equal to 0. So let's set z is equal to 0. Negative 4.9t squared plus 50t plus 100 is equal to 0. So I just give up and use the quadratic formula. And you should get 2 times here. One time would be negative and one time would be positive. And see how that makes sense, right? If this parabola were to extend back down in the negative direction, that's kind of like your negative time. So let's use a quadratic formula. B squared, or negative b, so negative 50 plus or minus the square root of 50 squared minus 4 times a, that's negative 49, so that makes it positive. Make sure that you don't get any imaginary numbers here. AC, or 50, yeah, AC times 100, all over 2a. So we should get a couple of times here. I'm guessing the plus one is going to give you the positive time. So if you're working that out, can you figure out the one with the plus and see what you get? So we get one value that's negative, and the other one is What is it? 11.9. Could we get a confirmation with that? Yes, confirmed 11.9. Just for fun, anybody figure out the negative? Negative 1.7. So we know that it's not the negative, right? Because it's going on the other side. So 11.9 seconds. So you're going to be in the air for 11.9 seconds, and you'll land in the ocean. Where? So we take the time that we found, t is equal to, let's put t is equal to 11.9, and put that in to the x and to the y. So, in fact, we can put it in to the whole thing, and we know that the z is going to be 0. It's 220.9, or wait, 229? Right, ish. So I've had a problem in the past where I would put a net of radius 10 somewhere that's not exactly at this point, and so you have to find out if you would land on that net. So you can move the net around a little bit, but the idea is if I give you a net, I would give you the equation of that circle, or I can say it's centered somewhere with radius 10. So let me say it's at net centered at, maybe I want to say 235 and 345. With radius 10. And I want to know if I land on that net somewhere. Let's make it a circular net. How would you find out if you would land on that net if all you're given is the center and the radius?
Well, we know that the net is in the x and y range of the given center plus or minus 10.
Right?
So if we've solved the answer, if we've solved for where we landed already, as long as those coordinates are within plus or minus 10 of both of those values, we want the net.
Yeah, so how would we do that?
Just subtract the answer.
Okay, subtract. When you say subtract, you mean kind of like find the distance, right? Yeah. So what you could do is if this is the center of your net, you could find the distance between these two things, where you landed in the center of the net, and if that distance is less than 10, then you're on the net. And if it's bigger than 10, then you're not. Okay? So if you add this part of the story, you can find distance between center and your landing point to see if it's bigger than or less than the radius. Okay, so you compare it to the radius, then that'll tell you whether you're within the boundary of the net or outside of the boundary of the net. All right? Okay, the review is online. It's in web access somewhere. I forgot where I put it. Under the notes from this week or last week? Last week. So under last week's notes, you can see the review sheet. Tomorrow, after class, I will put the solutions to that review sheet. And we'll plan to look over those problems on that review sheet in class tomorrow. So get a jump on it. Start by trying out those problems, and then maybe you'll get your answers question. Anna? 2 questions and a what? Okay.
So the first question is, are we going to bring a cheat sheet?
Yes, you get 1 sheet of notes back and front for the test, and you get to use your calculators. Second question?
Do we have test collections?
I allow 1 test correction out of the 2 midterms that you're going to take. And then the final, there's no test corrections because that's the last that we do. But you'll get 1 test correction out of the 2 that we are going to take.
Okay.
In your opinion?
Since we learned this today is going to be the test, I think it would be great to have 4 days specifically.
Thank you for your opinion.